Now we are recorded for eternity.
All right. Thank you. So, yes, as I said, I'm going to be. Thank you very much for the invitation to give the talk. And as I said, I'm going to be talking about conformal bootstrap and light ray operators. And I was given to understand that the audience, I should assume that the audience is rather mixed. And so I'm not going to go into a lot of technical detail, I guess, on these topics. But if you have technical questions, then of course, by all means, please stop me and ask, and I can give more details then. Now, let me start with some motivation. And as you might guess, conformal bootstrap is about conformal field theories. So I want to discuss quickly why do we care about conformal field theories at all? And in short, conformal field theories are quantum field theories with conformal symmetry. And very often, because conformal symmetry is conformal transformations are transformations of spacetime, which locally look like rescalings and dilatation, rescalings and Lorentz transformations, or rescalings orientations in Euclidean signature. Because quantum field theories themselves are local, it often happens that if you just have a quantum field theory which is scale invariant, not necessarily conformally invariant, it often implies that it is actually also conformally invariant. And this is important because it's easy in physics to, well, not particularly easy, but relatively easy in physics to come around with scale invariance. And this can easily happen if you take some sort of scaling limit. And in the scaling limits, not only scale invariance comes out if you have some kind of fixed point, but also the kind of a continuum description in terms of field theory shows up. For example, it's not necessary for you to start with a quantum field theory to end up with a CFT. And to give a concrete example and to have some kind of case study maybe for the rest of the discussion, let me describe Ising CFT just in case you do not think about it every day. So Ising CFT, in order to define it, let me first start with the Ising lattice model, which is defined by cubic lattice. And at the vertices of this cubic lattice, we have some spins, which can only be aligned along one axis, either up or down. We denote the spin sigma I. And so we can take essentially values plus or minus 1. And we also denote the lattice spacing by A. And given some configuration of the spins, we assign this configuration an energy E of sigma I, which is just given by sum over neighboring spins, minus j times sigma I sigma j, where j is some Stochastic positive coupling constant. And what this energy means basically is just that for in order to minimize the energy, you want to make all the spins align. You want all the spins to point in the same direction. The energy and the configurations in which spins point in random directions, these have higher energies. And so with this kind of energy for our configurations, you can compute the partition function, you can compute correlation functions, let's say, of spin sigma at site I and spin sigma at site j, using the usual formulas at temperature T. And so this is a statistical system, just classical. And we are interested in this case in the scaling limit of these correlation functions, where we take the distance between the kind of points where we perform the measurements D, we take it much larger than the lattice spacing A, and also we assume that it still is much smaller than the size of the system. And it turns out that in this kind of scaling limit, there are three essentially different cases. If you consider, we take low temperatures, if you take temperatures which are high, which are higher than some critical value, then thermal fluctuations dominate, and the fluctuations at point I is essentially independent fluctuations at point J, which leads to the correlation function being 0. And the corrections to this 0 turn out to be exponentially suppressed in the distance. On the other hand, if you go to low temperatures, the thermal fluctuations are small and the system is mostly ordered. And so the spins tend to be aligned at I and j, and the correlation function is 1, again with some exponentially suppressed corrections. But there is some critical temperature at which the phase transition happens between disordered and disordered phases. And at this critical temperature, the correlation functions decay only as power laws. So in particular here, we're going to get some constant times d over 8, some power, which can be written in this way. And this number delta sigma is going to be important what follows. And using conformal bootstrap, it's known to relatively high precision. And I'll mention how this comes about briefly. And in this limit at large distances, one can sort of define continuous field sigma of x, and sort of from this kind of discrete correlation functions define continuum correlation functions, which for the 2-point function will now take this form. In this way, we can get some clearly scale invariant correlators from a lattice system and some scaling limit. And for what follows, it's actually going to be important that sigma in this case is not the only thing that one can measure. One can perform other local measurements, such as you can define, for example, an operator epsilon I, which is just which involves kind of it's localized near sigma I, but it also multiplies it by sigma j from all neighboring points. And by repeating a similar procedure, we get some kind of continuum field epsilon of x, this 2-point function, which also is a power law, but now with some other power, which has which is known to similarly high precision. And so what we mean by Ising safety is basically a collection of all such scaling fields that one can define in this theory. So sigma, epsilon, and some others, infinitely many others, and their correlation functions, and not just 2-point functions, but 2-point functions, 3-point functions, 4-point functions, and so on. And they happen to be conformally invariant. So this collection of data defines for us what we call the 2-dimensional Ising safety. And in this case, this 2-dimensional Ising safety appears as a kind of in a scaling limit of this particular lattice model. But it turns out that it's more general, and in the example of 3D Ising safeties, you can think about this 3D Ising lattice model as a model of uniaxial magnets in which spins can only lie along fixed one axis. And it turns out that you don't necessarily have to use Ising lattice model. You have some freedom in perturbing this lattice model. You can consider other lattices and so on. And they all will have critical point, some phase transition, which is going to be which correlations are going to describe with the same data as 3D Ising safety. And moreover, this universality is well known to be much wider. We can have Ising safety appearing in liquid vapor transitions, even in water. At the end of liquid vapor phase transition phase diagram, there is a critical point where the safety is that you get is again 3D Ising, which is amazing. And this is kind of a perspective of statistical physics, but for any Euclidean safety, like 3D Ising, it's always possible to find a weak rotation to analytically continue correlation functions into safety in Lorentzian signature. And so this would be a conformal field theory now in 2+1 dimensions. And it also is related to various systems. In particular, now it describes some dynamics in real time. And it can be related to some quantum critical points and of classical critical points. And in the case of 3D Ising, 2+1 de-Ising, one can think about it, for example, as a phi to the 4 theory in 2+1 dimensions with critical coupling. So there's the CFT, which has this many various appearances. And in Conformal Bootstrap, we focus on this CFT with the idea that if we learn something about this conformal field theory, we therefore learn something new about this variety of theories. this variety of scenarios in which it appears. And this discussion was about 3D icing and critical phenomena, but there are, of course, many other CFTs. For example, there are OM models, which can be constructed in a way similar to icing, but now with some vectors and component vectors instead of sigma equals ±1. There are, of course, numerical models, various gauge conformal theories, such as Peng-Zaks, Chen-Simon Symmetry, etc. There are interesting conformal field theories with supersymmetry, which have very interesting kind of mathematical properties and so on. And of course, all these models themselves appear in other kind of classical quantum critical points. For example, O2 model describes lambda transition in helium-4 and so on. They can also be used to get some understanding about theories which are perhaps not conformal, but close to conformality. So one can try to use conformal perturbation theories, things like truncated conformal space approach, which is some numerical technique for studying conformal theories perturbed by relevant deformations and so on. They also appear in some models of beyond standard model physics, and last but not least, in EDS CFT correspondence says that quantum gravity and asymptotic length to the Sitter space in D+1 dimensions is exactly dual to CFT on the boundary of this, to D-dimensional CFT on the boundary of this space. And so this is a lot of various interesting applications of CFTs, various interesting scenarios in which CFTs appear. And the philosophy of Conformal Bootstrap is to kind of describe CFTs in themselves using some axioms and understand their properties, and use this to then these properties can be applied in all these scenarios. So in Conformal Bootstrap, we fix a simple set of axioms, and we try to use these axioms to understand conformal field theories and perhaps try to solve them. And to a large extent, this turns out to be possible even in higher dimensions, like in 3 dimensions and so on. So let me describe in 2 words what are these axioms, unless there are any questions about the motivation why we should care about CFTs. Okay. So as I said, conformal field theory is described by some set of local operators or local fields that we can measure, and their correlation functions. The set of all their endpoint correlation functions, which are conformally invariant. There also we assume that theories are unitary. Not all statistical systems are described by unitary theories, but all real-time systems described by unitary theories, and many statistical systems also satisfy unitarity. And in the language of this data, unitarity just means some positivity conditions on the correlation functions. And finally, the strongest axiom is the existence of convergent operator expansion, operator product expansion. It also defines some kind of completeness property for the set of local operators. And this axiom says that if you have a correlation function which involves 2 local operators, then it can be rewritten as a correlation function with fewer operators, where we replace this O1, O2 product by a sum over all operators OK with some coupling constants and kinematically determined coefficients. So there schematically have 2 operators in space-time, and we make them approach a single point. Then they almost, you can think of them in the limit when they meet at this point. You can think about them as some kind of local measurement. And so they should be expandable in our usual basis of local measurements with some structure constants. In general QFTs, this is considered to be an asymptotic expansion, but in conformal field theories, it's known to have a finite radius of convergence.
Sorry, this is in Euclidean space.
Yes, so it's the simplest to state in Euclidean space. And in the Euclidean state, the question, it also works in Lorentzian signature because the correlation functions are the same. It's just they are analytic continuations of each other. The question is really about the radius of convergence. And in Euclidean signature, the statement of radius convergence is simple. We expect the P to converge at least if we can find a sphere. Well, this is a very poor sphere, but we can find a sphere around this place where we want to do the OP such that no other operators are inside the sphere, then we believe the OP is convergent. In Lorentzian signature, the OP, the statement can be formulated as that the OP converges when the two operators O1 and O2 act on the vacuum functions, but does not necessarily converge in other situations. Does this answer your question? Okay. So let me just say a few basic consequences of these axioms. So first of all, the local operators, one thing that you can do to local operators is you can take their space-time derivatives. And based on this principle, you can separate them into two categories, which one are the primary operators, which are not a derivative of anything local, and then everything else are their descendants. So there are some space-time derivatives of primary operators. And this is a bit of oversimplification. The primaries also are defined to satisfy simple conformal transformation laws. And in particular, any primary operator, its transformation under conformal symmetry is described by a number, positive real number, which we call scaling dimension. And we saw examples of delta sigma and delta epsilon before. And an irreducible representation of the Lorentz group. Here I'm assuming that we have a CFT in D dimension, so Lorentz group is SOD minus 1, 1. And this irreducible representation is what we call the spin of our operator. So we can have some Lorentz index. So before we calculate examples of sigma and epsilon, which were scalars and had trivial, but more generally, we can have operators, and for this talk, it suffices to think about traceless symmetric operators. So operators which have J vector indices, which are symmetric and traceless in these indices. Example is the stress tensor operator, which is an operator with two indices, and we say it has spin 2, so by the number of indices. And using constraints of conformal symmetry, one can show that the 2-point functions in conformal field theories have very simple form. They are only non-zero between operator and itself. So for example, 2-point functions such as epsilon and stress tensor vanish. And when it's non-zero, it's just given by some fixed known function of scaling dimension, Lorentz representation, and space-time coordinates. So for scalars, we saw this is just 1 over x1 minus x2 to 2 delta O, but for operators with spin, it's more complicated, but still is perfectly known. And this is all great, but the best thing is probably this consequence of operator product expansion, which says that, well, this is just our operator product expansion, and obviously on the left-hand side we have n-point function because we had O1 and O2, and on the right-hand side we have n-1 point function because we replaced them by a single OK. So we have some expansion for n-point function in terms of n-1 point function, and using this we can always reduce our n-point function repeating the OP to a 2-point function. So in principle, using the OP, all correlation functions can be computed from the set of scaling dimensions and Lorentz representations and this coupling OP coefficients Fi, J, K. However, it's important that this is only true in principle, because if you say no and you find a subset of this data, you can, or even if you know all of it, and you sit down and you want to compute n-point function, you can only compute it where this expansion converges. And then you have to analytically continue it to the places where it doesn't converge. And if you want to know the n-point function in a place where the P expansion doesn't converge, then you are in trouble and you have to find a way to do that. Because if you only can do, for example, compute the sum on the computer, you don't know how to do this, analytic continuation in general. And I'll explain an example of this a bit later. But before that, let me just say a few words about what we mean by conformal bootstrap. So let's apply this idea. Right now, I just complained about this idea of expanding endpoint function in terms of n-1 point functions. But before going to situations when it doesn't work that well, let us first look at situations where it does work. So if you apply it to, say, 3-point functions, then we can take 3-point function of 1, 2, or 3, apply p to operators of 1 and 2, get the sum of operators OK with 3, and since only the 2-point functions only mean vanishing for identical operators, the sum is restricted to k equals 3, and we get that the 3-point function is just the p coefficient times some known expression. So 3-point functions are simple, as is well known in CFTs, and the first non-trivial correlations are the 4-point functions. And in 4-point functions, we can use several OPs to compute them. So we can take OP between 01 and 02. We'll get expansion, which will involve this coefficients f1 to k. And then there are expansions in terms of 3-point functions, but we just found that they have simple form. So in this case, we'll have f1 to k, f3 for k, and then times some known function, which can pictorially be depicted in this way. So it just describes exchange of OK in this OP 01, 02. And you can, of course, do other OPs like 01, 04 or 01, 03, which leads to 3 other kinds of expansion. And all these expansions converge almost everywhere in Euclidean space, and they can be equated to each other. And the fact that they should give the same function is non-trivial and is known as, these equalities are known as crossing equations, and they're sufficiently non-trivial, which is kind of very surprising that they give you a way to determine this delta sigma, delta epsilon, and Ising safety, for example. Let's see how this works. Sorry, is there a question?
Just these crossing equations for Ising work because you only have 2 primary operators, right? I mean, do you have to assume the spectrum of primaries to solve these equations?
Not quite. I'll explain in a second. But in Ising, you have infinitely many primary operators. It's just that sigma and epsilon are the most commonly discussed ones. So in the sums are always infinite in dimensions greater than 2.
Yeah, I mean, but they are primary and they are primary under a bigger group, right? Under Virasoro.
In 2 dimensions, they're primary under Virasoro, and because, well, in 2 dimensions, there, as far as I remember, actually is only sigma, which is primary under Virasoro, and there's sigma, epsilon, and identity, which are the primaries under Virasoro, and this is a finite system, and you can solve it. Now, in 3 dimensions and higher, we don't have Virasoro, we have a smaller group, we have global conformal group, and it has infinitely many primaries in all theories. You can check that these equations just cannot be solved with any finite number of primaries. So, and this is the reason why this is known with some finite precision, not infinite precision. So if you only had a finite number, you'd know this numbers much better.
One question, if I could, what exactly does unitarity or reflection positivity imply for these FIJKs? What condition does it impose?
So for FIJKs, it imposes essentially that they have a definite reality property. It depends, the reality property depends on the details of the operators, but for example, for scalars, for 3 scalars, it imposes that these coefficients are real. And you can show that basically, if you know that these coefficients are real, and you also know that this all the dimensions satisfy unitarity bounds, which I haven't talked about, but they're unitarity bounds in these deltas, then you know that reflection positivity holds. Right, so in particular, for this example where these numbers come from, to just explain it in short, let's take this 4-point function and set all four operators to be sigmas and take, say, this equality. Then we have the equality that expansion in one channel, which now involves squares of this OP coefficients because we set all operators to be sigmas, is equal to expansion in another channel. And important point is that since we know that reality, these coefficients are real because of unitarity, we know that their squares are positive, which you can also actually think of as a unitarity condition. And these functions are just the conformal blocks. Well, they are called conformal blocks, and they're functions which depend on delta sigma, which is the scalar dimension of sigma, and the dimension and spin of the exchanged operator. And they depend on U and V, which are cross ratios, conformal cross ratios, and these are just things on which 4-point functions depend. And the two conformal blocks, which appear on both sides, are essentially the same function up to exchange of these two cross ratios. And so these are some known special functions. There are algorithms for computing them. And the equation takes this form where you have a bunch of sum of a bunch of special functions with positive coefficients equal to 0. And the way you should think about this equation is you can interpret these functions as vectors in some vector space. And we're trying to find the positive linear combination of these vectors, which gives 0. And sometimes this is possible. For example, like in this picture, where you can, roughly speaking, just take all 3 vectors as coefficient 1 and it will give you 0. And sometimes it's not possible because in this situation, all 3 vectors sort of point in the same direction. The positive linear combinations only live in this shaded green region. And if you want to get 0, you have to choose coefficients of every single vector to be equal to 0. So there's a trivial solution when all f sigma sigma k are equal to 0, but it's not, of course, does not give a consistent theory. So it could be that this equation cannot have a solution if these vectors kind of arrange in some unfortunate manner in the vector space in which they live. And the way to detect whether this is the case is to try to find the hyperplane such that all vectors lie on one side of this hyperplane. And to be a bit more specific, what one can do is one can assume some value of delta sigma, and then assume some allowed range for delta k's and j's, and you don't have to specify all the delta k's. You can also work with just kind of say that delta k can be anywhere in the range from 0 to infinity, for example, and this will just give you some continuous families of vectors that you have to take linear combinations of. And then you can try to prove that these continuous families are on one side of hyperplane, and therefore the equation cannot be solved. And in practice, this is done by taking some taking derivatives of this equation in U and V at some particularly nicely chosen point, which gives you then kind of a finite dimensional truncation of this equation. And then the search for this hyperplane is just performed numerically. And the logic is simply that you make some assumptions about delta sigma, about the range of delta k's, and you try to prove that using this strategy, you try to prove that the equation cannot be solved. And this was first proposed by Rotazzo, Regge, Tony, and Vicky in 2008. And this is how these numbers for delta sigma and delta epsilon were obtained. In particular, this is a bit more complicated setup, but if you follow this logic for all correlation functions involving sigma and epsilon, all 4-point functions, then you find that you can prove the following statement. So you find if you plot the delta sigma, delta epsilon plane, then you can find this kind of domains, which are denoted and depicted in blue here. This is from this paper, in which the statement is that if you take any point in the white domain, so if you assume that delta epsilon and delta sigma have any value in the white domain, then using this logic I just described, you can prove that the crossing equations have no solutions. And if we take a point in delta sigma and delta epsilon in the blue domain, then you cannot prove anything. Maybe the equations have a solution, maybe they don't. You don't know. In any case, there are more crossing equations in the conformal field theory, so even these ones that you looked at can be solved, but the other can't. But the important point is that in the white region, you for sure know that there is no conformal field theory. And for Ising CFT, you know that it should be sort of here. And so you conclude that it must be in this blue island. And this gives you precise determinations of delta sigma and delta epsilon. Here, this is from an older paper, from newer papers, from more recent papers. If I were to plot the silent, you would just not be able to see it on this picture. It's very small. So this is the logic, and it's been applied to several theories, successfully determined scaling dimensions of some important operators. I'm not going to discuss this in a lot of detail, but let me just say that there is an interesting direction in this area, which is basically that the most studies that have been done of numerical bootstrap are working with correlation functions of scalars, such as sigma and epsilon, because these are the simplest. And on the other hand, there are many other operators which have spin, not just scalars. For example, there is stress tensor, there are spin-1 conserved currents, fermions, which are necessarily spinors, and such studies, not many such studies have been done. And this is mainly complicated by the fact that kinematics are more complicated when you have spin for the external operators. In particular, for example, these functions, these conformal blocks, they're much harder to compute, and they're not single functions anymore. Now they have a whole bunch of indices, and you have to compute them for every values of these indices. And you can be interested in doing such studies because not all theorists have just the scalar operators, for example. Not for all theories, just the scalar operators are important. For example, theories like Krasnovikava models have been studied using four-point function of fermions successfully and not just of scalars. And correlation functions like stress tensors and currents, they're just very universal because they're present in any conformal field theory or in any conformal field theory with some global symmetry. And a few of such studies have been done, but more kind of general research in this direction was impeded by this technical complications related to conformal blocks and tensor structures and so on. So over the past several years, we've been working on sort of developing technology for doing such computations. In particular, in the last 2 years, we have developed an algorithm for computing conformal blocks for any kind of operators in 3 dimensions efficiently. So any kind of external operator, so it doesn't have to be scalars on external legs, it doesn't have to be, it can be anything on the internal leg. And recently we published this paper where we described the software package for just, you can tell your computer, compute this conformal block, any conformal block at all in 3 dimensions, hit enter, and it will spit out the answer. And this very much simplifies the numerical study of such correlators, and we have some work in progress using various interesting correlator systems in 3 dimensions, and there's also some other research we've done which allowed us to do bootstrap in 4 dimensions with spin, and now they're working on things like 4 currents in 4 dimensions. I don't want to spend my time on this, and I want to move on to light ray operators, but if there are any questions, perhaps this is a good point to ask them. Okay. So far, this discussion was using this idea of greater product expansion to compute higher point correlation functions in terms of lower point correlation functions. And if you just look at the OPE, the thing that it does well is it describes well the short distance singularities of correlation function. What this means is that if you take two operators, O1 and O2, and they're separated by distance r, then applying the OPE to them, you get some expansion, O1, O2 equals to sum of our operators. And if you truncate them at truncate this expansion at some point, then the error that you make is kind of bounded by a power of the distance between these operators, where the power is determined by the scaling dimension of the operators that you discarded. So if you discard only operators with high dimension, you approximate this correlation function very well in small r expansion. So the OPE gives you kind of the leading short, finite number of terms in the OPE gives you the leading short distance behavior of correlation functions. And in Euclidean signature, these are the only singularities that you have. Because for when the points are not colliding in Euclidean signature, then the correlation functions are just some real analytic functions. They have some value, I don't know, 3.7150, but they're not something that they don't have any interesting behavior, except when the points start colliding. But in Lorentzian signature, you have light cones and other singularities. And it's interesting to ask what happens when some special kinematics related to light cones happens in Lorentzian signature. So for example, one famous limit of this kind is the Regge limit, which can be described in flat space as the fixed operators O3 and O4 in some positions, but you boost operators O1 and O2 to sort of to approach the same null cone. And in the picture, you can make a conformal transformation to the Lorentzian cylinder, and in sort of ADS-CFT style correspondence, this limit corresponds to high energy scattering in the bulk. So you have operators O1 and O2 kind of approach each other's null cones, and same happens for 3 and 4, and they're not just, and they're also null separated in the bulk. So this corresponds to some high energy scattering process in the bulk. And then from this picture, you can see that the operators O1 and O2 kind of have special kinematics between them. In particular, they're almost null separated in this limit. And so naturally, you would assume that perhaps to get some leading information about this kind of limit, you would take the OPE between O1 and O2, and you would figure out what is the leading behavior. But it turns out that in this case, this OPE is very divergent. And you can take other OPEs, for example, between O2 and O4, O1 and O4, but it turns out that while these OPEs converge, they don't have this property that they are not dominated by any particular operator in this limit, and they converge slower and slower as you approach this configuration. So while you can in principle compute the correlation function, it's not clear physically what is the quantity that dominates this process. So similarly to Regge scattering S-matrix theory, one can find the answer using Sommerfeld-Watson resummation tricks, but I'm not going to describe this in a lot of detail. This is just to motivate the idea that you need to analytically continue our OPE data, our structure constants and anomalous dimensions and spin. And just to explain why this is why this happens, in case you're not familiar with this trick, is that the correlation function that you want to compute can be written as sum over spins of the exchanged operators. We have the OPE coefficients, and we have some functions which depend on scaling dimension of the exchanged operator, which also depends on spin. And the divergence here comes from divergence in this Regge limit comes from large spin, large J. And the trick that one performs is to rewrite the sum, assuming that these functions can be analytically continued away from integer j to complex j. Rewrite the sum as contour integral over j around these points where we perform the summation, and then deform this contour to something which has bounded real part of j. And once this real part of j is bounded, one is free to go to Regge limit, and this expansion will behave nicely. But now the asymptotic and Regge limit will be determined not by f, say, the SOP coefficients to any particular integer value of spin, but by their analytic continuation. And this is the kind of motivation that for light-ray operators, they explain in some sense why we expect that the OP data and spin, like the OP data, the OP coefficients and normal dimensions can be analytically continued in J. And as I'll explain in a second, what happens is that the reason why we think this is possible is that we can write some expressions for local operators, which have some integer values of spin and some generic values of dimension delta. But we also can write expressions for some non-local operators which interpolate between these operators, and they have non-integer values of spin and similar values of dimension, and they are the things that dominate Regge limit. However, as I say, this is true perturbatively, that we can write these expressions, but I'll refer to them as light-ray operators, to these perturbative expressions, and I'll discuss how non-perturbative is this result in general. So to just give you an example, let me first start with local operators in Wilson-Fisher theory, which is phi to the 4 theory at critical coupling in 4 minus epsilon dimensions. So in particular, if you set epsilon to be 1, you get 3-dimensional Ising-Swift, as we discussed, and the operator phi, which is the fundamental field, corresponds to sigma, phi squared corresponds to epsilon. So in general, the local operators in this theory are some polynomials of field normal ordered polynomials of field phi together with some space-time derivatives. So as we discussed before, in CFTs, some of them are going to be primaries and some of them are going to be descendants. In particular, if you filter out the primaries from this expansion, the simple primaries that we get are phi, phi squared, and also operators, for example, of the form phi, a bunch of derivatives phi, to which we add some total derivatives to make them transform nicely under conformal group and subtract some traces to make this operator reducible. Now denote these operators by OJ, mu1, mu_j, and their importance is that they have leading twist, so they have, in other words, they have the smallest scaling dimension for given spin. And for example, the case j equals 2 is the stress tensor operator. So these perturbative light-ray operators that analytically continue between, in some sense, interpolate between this particular family of local operators can be perturbatively written in the following form, where we have again something quadratic in field phi, normal ordered, but now we have some null vector z, and we're integrating this phi along this null line. It's 2 points, and their separation is beta, and we have some wave function which depends on beta, and we're integrating along all possible insertions of phi in this null array. So this is just some expression that you can write, and the reason why this expression is nice is that for integer spin, for integer j, it is related to these derivative operators that we just discussed. The way this happens is that if you set j to be an even integer, you can check that this function here as a distribution, it tends to a delta function, and to a derivative of a delta function, and it starts taking derivatives with respect to beta. So after total derivatives, the expression in the integrand can be written in this way, and total derivatives drop out because of integration over alpha. And comparing to this expression for our local operators OJ, we find that these guys reduce to some null integrals of OJ, where we use this index-free notation, where O of x and z is just O of x contracted as vector z. And the point of this is to show that there are some concrete expressions that you can write perturbatively, and these expressions have been studied for quite a long time, and I'm not even sure where they first appeared. And these expressions reduce to local operators at some special values of j, and you can even renormalize them, compute their anomalous dimensions, and so on, and, for example, interpret them in terms of Regge theory. However, an important question is how non-perturbative are these operators? In other words, what can we say about, let's say, a Regge limit non-perturbatively? And there are several reasons to care about this question. For example, first of all, we actually do care about things like Regge limit and other observables that I'll mention in a minute. And we would like to understand them for general CFTs such as Ising CFT. Now, Ising CFT is this Wilson-Fisher theory at epsilon equals 1, but this is, of course, not a perturbative situation. And so we would like to have.
Can I ask you a question just to orient myself? So what part of this is novel? Or maybe you're coming to something novel. So
I'm coming to something novel, yes.
Thank you.
So perturbatively, people have studied this for a while, but the question is sort of the contribution that I'm trying to describe is that we have now some non-perturbative understanding of these operators, and which is also kind of Lagrangian free description. The idea is that we have this nice axiomatic description of conformal field theories, and just from this axiomatic description, as I described, we can pull out this precise numbers, for example, about three-dimensionalizing. And this is nice both theoretically and practically, because we can theoretically satisfactorily sort of isolate some theories, prove that there are only such theories with such properties, compute their scaling dimensions of e-coefficients, not relying on any approximation schemes. And the Symmetry operators, they describe things like Regge limit, and we would like to understand, say, Regge limit in the same way. Can we understand Regge limit of something like 2+1 dimensional Ising CFT rigorously without approximation schemes in the same way as we understand the local correlation functions, like the scaling dimensions and peak coefficients in numerical bootstrap. And another reason to want non-perturbative understanding of the Symmetry operators is that they interpolate between local operators, and the spectrum of local operators is really complicated, and we don't really understand any structure. Well, we have some ideas, but we don't completely understand the structure of the spectrum of local operators in conformal field theory. So having some Regge trajectories which connect the operators amounts to some interesting structure in this space, and it's important to understand it. For example, in 2D, we have very thorough symmetry which organizes our primary operators, but there's no such things in 3 dimensions, and perhaps these Regge trajectories could be the second best option for any kind of organization of the spectrum. And this question, so it wasn't really understood. I don't think anything non-perturbative was understood about these operators until recently. So the progress started with this paper by Truncated in 2017, where he derived an analog of Rosard-Gribov formula for conformal field theories, which gives a multi-continuation of partial waves of conformal 4-point functions in spin. And what we found in our paper from 2018 is that one can, first of all, there is natural generalizations of this formula to general correlation functions, which is very suggestive. And if you look carefully at this formula, you find that you can actually interpret these expressions that Kravchuk derived and derive new formulas which actually give a definition for light-ray operators in non-perturbative conformal field theory. And the definition takes the following form, as written here, where we take some kernel, which is some kinematically determined kernel, depending on x1 and x2, and the arguments of the light-ray operator, which is a space-time position on a null vector. And we take an integral of a product of two local operators. It doesn't matter which ones, but some pair of local operators. And we get some function of delta and j. And this function will have some singularities in complex delta plane. And if these singularities are poles, then you can take residues of these poles. If they're cuts, you can take discontinuities. And these singularities will define for you the light-ray operators. And you can go, for example, to these perturbative examples and apply this formula, and you reconstruct the same formulas as I shown before. But now the statement is that you can interpret this non-perturbatively in general CFTs. In particular, you can compute the matrix elements of these operators and between states created by primary operators and have non-perturbative formulas for them. And also, this gives sort of a conformally invariant generalization of these light-ray operators to which exhibits their conformal properties. And it turns out that they have the same arguments as local operators, so space-time position and polarization vector. And the relation to local operators is that integer spin. They're reduced to, sorry, they become equal to light transform of a local operator, where a light transform is some interesting integral transform, which is essentially a conformal generalization of this null integral. And it's related to some interesting representation theory and Knopfstein intertwiners conformal group. More generally, you can ask what is the global picture of these Regge trajectories in something like Ising model in Wilson-Fisher. And you get, there's some work in progress that we have in this regard. And the picture that you get is roughly the following. We have, first of all, one can show that in these coordinates where you have spin here and delta minus d over 2 here, there's always a symmetry. It's called shadow symmetry, which relates the two sides. So this picture has to be symmetric. And then there are some local operators which leave at integer spins. And it turns out that it's important that a single family of light-ray operators only interpolates between operators of even spin parity. So here the local operators only appear at even integer spins. And we have this, for example, the leading Regge trajectory, it has an intercept at kind of the minimal value of j, which is responsible for which describes the asymptotics in the Regge limit. There are some generalizations of Regge limits, which then is dominated by a light-ray operator anywhere in the leading Regge trajectory. There is an interesting story about how this picture appears from the free theory, and it turns out that in free theory there are light-ray operators which live on this 45-degree trajectories and on this anti-diagonal 45-degree trajectories. And then there is some interesting mixing problem in perturbation theory which happens at this intersection, and which can be resolved to give this Regge intercept. Similarly, there also turn out to be some interestingly Regge trajectories which are horizontal and they're not really related to any local operators, but they kind of interplay with other Regge trajectories. And it looks like when you look at this perturbatively that there is a possibility that in some sense there is a singular Regge trajectory and all of these different ones are just different branches of it. And I don't have time to get into the details of that. Let me just mention that in the remaining time, that another result that we found is that on this Regge trajectory, there are integer points at 2, 4, at even integers, which are local operators. And we all know what local operators are good for. But there is also, interestingly, points at odd integers, which are not related to local operators, but turns out that they are important for things like energy-energy correlation functions. And by energy-energy correlation functions, I mean observables of the form of this form. Suppose we have some state which can be described as some event happening at time equals 0, somewhere in the center of our space, and then some radiation is flying out. And far away at infinity, we insert calorimeters in directions n1 and n2, which are denoted by epsilon, which is separated by angle theta, and they just measure the energy flux which passes through them through the entire history of our system. So this kind of observables are interesting, for example, in colliders. People care about them and use them, for example, for studying for determinations of strong coupling constant and so on. Of course, here we're studying them in conformal field theory, where setup is simpler, but I think it's still interesting, and we have some interesting interactions with people from amplitudes community. Right, so the question that we studied with regard to these observables is whether we can find an OPE for these detectors, which would describe the small angle limit of the correlation functions of two detectors, of two energy detectors. And it was suggested by Hovnum, Moldasena, in 2008 that Leitra operators is spin 3. So it's kind of the wrong parity for it to be related to a local operator, that such operator should be describe the leading term, qualitatively at least. And in our series of papers from last 2 years, we actually found a complete expansion for this kind of observables. And here is an example for so the left-hand side contains sort of a simplified version, which involves sort of a scalar annex of energy, just because schematics are simpler, but we also understand it completely for the energies. So I'm not going to decipher the notation completely because I don't have time and it's not going to be very illuminating. But the point is that we have complete formulas for the energy-energy OP and other kind of asymptotic observables in terms of the Leitra operators, and the interpretation of their anomalous dimension then becomes kind of the encoded in these powers of the angle that appear. Also, there have been work by Karchemsky, Dixon, Moulton, Zhu, which studied the leading term, but we managed in 60s at least to find the complete expansion. I'll end here with some open questions. So one important open question for this story, I think, is to understand whether these partial waves for conformal field theories have only poles. In other words, can we describe all in this formula that I've written for Leitra operators, you had to take residues or discontinuities, and the question is, can you always take residues, or do you always have to, or do you sometimes have to take discontinuities? And this is related sort of to the structure of Regge trajectories, in the sense that they're isolated trajectories, or are there some sort of surfaces instead of trajectories? And this is kind of the question of whether there are Regge cuts in CFTs. And for that, I think it would be interesting to study Leitra operators involving more powers of pi. Finally, I think, furthermore, I think that an interesting question is to try to determine some Lorentzian observables in non-perturbative CFTs, such as Ising, to precision which is similar to what we know about Euclidean observables. For example, one concrete thing we can try is to determine energy-energy correlator in 2D using numerical bootstrap. And for that, it will probably be helpful to do numerical bootstrap on sigma T system and try to find out the continuation of the data that we can extract from there. Another point is that at least perturbative description of this trajectory suggests that there's some interesting global structure where the trajectories which are independent in free theory in tracking theory are combined to become different branches of a single trajectory. And one can ask whether anything can be learned from the global structure of the trajectories. Perhaps, for example, one can get some maybe at least new techniques for computing, let's say, anomalous dimensions perturbatively, because if you try to compute anomalous dimensions of this trajectories, you will find that they have, as functions of spin, they have poles at the points when these trajectories intersect other Regge trajectories. And maybe by understanding these poles, you can understand something about the anomalous dimension in general. Finally, sort of a more open-ended question is that both the Regge limit and this energy is some kind of operator product expansion between two operators, two local operators. In this case, it's stress tensors, and Regge limit it's anything else. And in both these cases, in all these examples, it turns out that when you cannot write the P in terms of local operators, you can write it as some kind of sum or integral over Elytra operators. And one question is whether there is just one kind of unifying operator product expansion formula which expresses product of O1 and O2 in terms of Elytra operators, Lorentzian signature, such that all of these examples follow simply from this expression. All right, I'll end here. Thank you for listening.
Okay, thank you very much for this illuminating talk. So now it's time to ask questions. Please do so.
So may I ask a bit more about this Regge trajectory? So what is understood about them? Is, like, for instance, is every operator belongs to some Regge trajectory? And like for these even spins, you say that that's where local operators appear, but does it have necessarily to be a local operator for each even spin? And
right, so maybe I can give a bit more technical detail here just to answer this question. So what is known is that you can, let's focus on a matrix element. You have some O, let's call it O3, and then you have here Elytra operator, and then O4. And so what this means, what this equation here means is that you write this as, can write this as a residue in delta of some function C of delta and J. And the thing that is known, things which are known rigorously are known about this function C delta J. And it's known that for even integer J, this function C delta J has, it has poles in all kind of positions of local operators. So that's known. And it's known that this function admits analytic continuation in J, like distinguished analytic continuation in J. However, it's not known in general what is the structure of the singularities for general J. So simplest picture is that the poles, they just move as you start changing J, and then you have isolated Regge trajectories, but we don't completely understand this question. And but yes, for integer J, it's definite that these are local operators, and whatever this formula defines is related to these local operators at this point.
Thank you. Are there other questions? And I can ask one, the analyticity or continuity and analyticity in J of the slide con operators, is it assumed or is it a consequence of other axioms in the conformal field theory?
Well, I wouldn't say it's consequence of axioms because, you know, when you use the word axiom, there is certain standard attached to how you derive things from axiom. But so the real question, which is appears to be the hard question, is to understand this, the structure of this function at the structure of this function as a function of delta for some non-integer values of j. And depending on, no matter what the structure is, any non-analyticities of this function are expected to be universal and related to some sort of non-local operators. But for example, for simplicity, if you assume that the non-analyticities are just poles, then the analyticity in J, of course, just comes out simply because you have an analytic function of two variables, and what you've done is just taken residues in one of the variables. And so the analyticity of all the properties, well, for example, the anomalous dimension just becomes the position of the pole, and of course, if you have a function, homomorphic function of two variables, which is meromorphic in one of the variables, then the position of the poles are analytic functions of the second variable.
Okay. So, do we have any other questions?
Peter, I have a question. So mostly related to the first part of your talk. Suppose you have some deformation of the CFT, so you break conformal invariance weakly in some sense. I guess that depends on scale, but my question is, can you use bootstrap techniques to study deformed CFTs also, or is it really for pure CFTs only?
Well, one thing that you can do, of course, which is probably a trivial answer to your question, but you can, if you know you can use bootstrap techniques to study CFT which you're deforming, and then you can try to use conformal perturbation theory to understand deformation, or you can try to use the truncated conformal space approach, which is you take the idea of this approach is that you take the basis of the Hilbert space, which is given by conformal primaries, and then your rewrite perturbation is integral of some primary operators. And you can compute the matrix elements of kind of your perturbation to the Hamiltonian because you know the matrix elements of all the primary operators. So the Hilbert space is completely spanned by states created by a single insertion of a primary operator. And so because of that, you know all the matrix elements, and you can then try to diagonalize this perturbation numerically. This is what some people are doing. And I guess it's a bit more far-fetched to do this for interacting conformal field theories because you really need to know a lot of OP data, but if there's enough progress, you can imagine that something like this can be done.
But so similarly, you know, you can build up all the higher point correlation functions if you know the 2-point functions, let's say, or the.
Well, I think the question of whether the operator's expansion, operator product expansion is convergent in theories with a scale is not. It's not clear because, you know, you expect to be close to CFT when the energies are large enough, and so especially short distances, so you expect to have the CFT the same OP as in CFT essentially, short distances, but then at longer distances, it's not understood whether it will converge or be just asymptotic.
Right. So, but you know, if you introduce some mass, then there's some expansion in the mass times the separation, m times r or something that you can do. but can you do that perturbatively still? Let's say where it's approximately, at short distances it converges to this, or it asymptotes to the CFT, but then there's a sense
Right, so
in
that
which
would
for
be
some
a-
distances it's still weak perturbation, right?
Yes, so I think that would be essentially the conformal perturbation theory, which treats the masses, mass parameter as perturbation.
Thank you. I can add that there is even a simpler way in which these methods are important to study deformations. These methods can determine the dimension of primaries. So if you have a primary that say has dimension 1 in a free theory or in perturbation theory, it may not be, well, dimension equal to space-time dimensions, say delta equal to D. It may be, it's very important to know whether the delta is less than D or larger than D, because in one case, the deformation is relevant, and then at low energies, you go away from the fixed point. Otherwise, it's irrelevant. So already that is important, and Piotr can say more, but I think it has even practical applications in determining whether there are certain particular deformations of conformal theories that we use actually in condensed matter, whether there are phase transitions in helium or something like that. So just determining dimension is very important.
Yes, I haven't discussed this, but very true. So in general, you can think about sort of the set of RG flows of theories, and conformal theories are important points in the space of RG flows. And if you have some kind of RG flow, you conjecture that it ends in some theory, then you can check this conjecture by studying the scaling dimension of this theory, how the operators, for example, if you say that you have some system, let's say you have Heisenberg ferromagnet, and you say that there is a phase transition, and this phase transition described by O3 model, then what you have to check is that all the operators which are sort of singlets under the symmetries of your lattice and so on are still like all the relevant operators which are singlets, that you have tuned them to the critical point. And recently there was a very interesting work which showed that actually it's not true that Heisenberg magnets are described by O3, because O3 has a relevant operator which is singlet under the lattice, but is not, but of course it's still scalar under O3. Sorry, but it's charged under O3, and most likely their G flow from Heisenberg magnets ends at another fixed point. But this operator is like very, very weakly relevant, so it wasn't known for sure before.
Thank you.
Thank you. By the way, at some point, Ken may take over and decide when to stop the recording, because I'll have to leave at some point. I have an appointment at 4 somewhere else. But first of all, let's thank Piotr again, and then we can continue the discussion. So please continue and ask more questions.
Does anyone else have a question?
So in ADS CFT, the intuition behind these Regge trajectories is what, just kind of particles rotating around each other in ADS space, something like that?
Okay, very good. So this intuition that you're mentioning for ADS, it applies to this notion of double twist operators, which I haven't discussed. So there are some statements in CFT that if you have two primary operators, O1 and O2,
yeah,
and they have twists tau1 and tau2, then there are families of operators, and L. People kind of denote them in this way, but it's not really a product. It's just a statement for any pair of O1 and O2, you can construct these families. And the property of this family is that it has spin L and twist tau1 plus tau2 plus 2n plus L. sorry, just plus 2n.
Mhm.
And the intuition for this kind of operators is indeed what you say that, well, sorry, it's not exactly this, of course, plus gamma of L, and this gamma of L goes to 0 as L goes to infinity. So at large spin, these operators exist. And the picture for this is indeed, if you think that one operator creates some kind of blob inside of ADS, then another creates another blob, and large spin means that they spin around sort of high angular momentum, which means that they're separated far enough and are weakly interacting. And this leads to this kind of picture where you have just their twists add and the anomalous dimension describes sort of weak interactions between these two blobs.
But this would be a double trace operator, right? So, but in your trajectories, which you're talking about, they're not like that, right? So they're.
Yes, that would be double trace. Oh, this, when you say double trace, it's usually in the context of some kind of gauge theory where you have traces
Right,
and so on.
But in
Again,
ADS context.
Yes.
But so, but these Regge trajectories you're talking about, those are not necessary. Those can be single traced operators, right? So
yeah, those are not necessarily with this one. They can be single trace, and people studied them, for example, in single trace trajectories like twist-2 operators in QCD. This is, of course, not a CFT, but kind of continuous spin twist-2 operators in QCD are related to sort of evolution of non-integer moments of Parton distribution functions. And
so what is the intuition behind the existence of these Regge trajectories? Is there any?
oh, first of all, you can perturbatively write them and study them. Then there are, of course, Regge trajectories. Like one strong example, I guess, is in n equals 4, the single trace operators. You can find their spectrum, and people have found the Regge trajectories. And there are some nice pictures you can find this integrability papers where they plot the entire complex surface of this leading twist guys in planar n equals 4. But more generally, it's this idea that it all comes down somehow to this idea that you have this function, and you know that integer j has a bunch of poles which relate to the local operators, and then you know that it can then continue to non-integer spin, and something should happen to this poles. So even for single trace operators, this pole has to either move somewhere and from a trajectory, or maybe become part of a cut or something like this, but something should happen, it cannot just disappear. So some sort of Regge trajectories exist, but it's not clear whether they're like isolated pole trajectories, or maybe there are some cuts.
Yeah, but I guess in ADS it's more like to summarize. It's if there is a string states dual to which live in ADS, that would be really Regge trajectory, like corresponding to some rotating string in ADS, which wouldn't be. I think that's how it is in n equal 4. So it's not. It can be single trace, but because it's a single string, but then it rotates and gets longer and longer, and these are what this Regge trajectories physically kind of in this.
Yeah. Well, I mean, for single trace operators, as long as you're talking about integer spin, so when you say string in rotating string in ADS, you mean, I guess you mean integer spin, because
right, yeah,
it has to be quantized in this picture.
Yeah.
And for integer spins, I mean, if you have some particular theory in mind for which you have a distinction between single trace and multi-trace, you can see whether you can find some trajectories of single trace integer spin operators. Because the question is why they have to sort of be there. But,
yeah.
I guess, yeah, rotating string is a good point of view. I mean, I'm just more used to thinking about sort of more general CFTs, in which case there isn't necessarily a meaningful distinction between single trace and multi-trace. There is the structure which I described about multi-twist operators, and they give another sort of piece of evidence that we expect the spectrum to be organized in trajectories. But this is also not entirely rigorous at this point. So there is an open problem to understand how statements like this can be made completely precise.
Okay, thanks. I have to go now, but thank you for the talk.
Thank you, Petr. That was a great talk. Yeah. So I think, yeah, we'll head out there. Thank you so much. And we will be in touch, of course. Yeah.
All right. Thank you. Bye.
Bye, Petr.